up in room 5 after school, so we can answer any questions then. Yeah. As you go through your homework, things come up again.
You have something on your sheet.
What the heck? Dryer sheet? That's funny. Okay. So where did we finish off last time? Let's just do a quick recap leading up, covering some of the big stuff we did before we continue from last time. So first off, we introduced the idea of what's a random variable. A random variable is just a function whose domain is your set of outcomes from your sample space. And the output is
a set.
Just a set, doesn't matter. We don't know anything about it, it's just some set. A real random variable, or your book probably says like a real valued random variable, something to that effect, is just a random variable whose codomain is a set of real numbers. So the image is going to be a subset of real numbers. Didn't lose you so far? Nice and easy. Okay, then we got to expected value. Expected value only made sense when we were talking about a real value random variable. You can only take the expected value of a real value random variable. Otherwise, it doesn't make sense. Okay? So, if you have a real random variable, x, from our set of possible outcomes to r, then we define the expected value. That's not the definition. Oh, I skipped. We're up here. So if we have a real random variable x from our set of possible outcomes to r, the definition of the expected value is the sum of x of s times its probability for every possible outcome.
Okay.
Take the real value times its probability and do that for every possible outcome. Sum those up. That's your expected value. So the expected value of rolling one die was 7 halves. We would roll 1 1/6 the time. We would roll 2 1/6 the time. We would roll 3 1/6 the time. If you add all those up, you get 7 halves. Still with me?
Yeah.
That makes sense? Quick recap. So, calculating random variable. Then we have this theorem, which is where I felt like I was losing you guys last time. That says the expected value is equal to this summation. So for every real number, take the probability that the random variable equals that real number, multiply by that real number, and add those up. And that is also the expected value. So notice.
So can we prove that?
Yeah, we proved it.
I know.
Last time. We started with this,
Okay.
and we kept manipulating it until we got to this. And I did that big sum, and we did an example on the side as we went. Rewatching that and following what I did is going to be so useful to you guys because you are terrible at manipulating sums. This is such a high level of abstraction for you, it's hard for you to keep up with me when I start manipulating these things.
Yeah.
So if you were to go watch that again, watch how I went from this to this, come up with an example of your own and write out a physical example as you went step by step, seeing what's happening, that would make a world of difference for you in being able to handle these sums, to start seeing what's happening. Because I can tell every time I use these things, it's like I opened a black box. And you guys are just waiting to find out what the answer is, and you could care less about the steps in between. So, you need to learn how to use sums. They're so useful. I mean, because this right here, we're representing an infinite sum right here. It's just, there's no good way to not do it. So anyways, let's try to make intuitive sense of it again. We're saying that the probability that x equals a, which means that x is spitting out a here, right? Anytime we have a probability here, anytime this number isn't 0, is because x was equal to a, right? So this a is replacing that x of s. If x was equal to a, that means x of s was a.
Okay.
So we're grouping up. See, this, if I were to write out the sum, it's possible that a bunch of these x of s's gave me the same number. Right? It's possible that a bunch of those gave me 1, a bunch of those gave me 3.5, a bunch of those gave me 10. Oh crap, we erased the example I had over there. But I think even in that example, 2 of them gave 3 or something. Anyways, it's possible for this to repeat a value over and over and over again, several times, right? So maybe let's say that the first one comes up 0.1% or 10% of the time. So let's say that we have 3 from this function. We have 3 comes up 0.1 times, 3 also comes up 0.2 times, and 3 also comes up 0.1 again. So what this is doing is it's saying, look at all the times that 3 came up and calculate the probability that x gave you 3. So instead of writing 3 times 0.1 in this sum, and 3 times 0.2, and 3 times 0.1 again somewhere else, this is saying do 3 times the sum of these probabilities. That's what going from here to here is intuitively doing. But it gives you the same thing. Does that kind of make high level sense?
Yeah, that's correct.
But once again, actually going through that sum, doing a physical example, it helps so much. Okay. And then we did this proof. We proved that the sum of the expected values is equal to the expected value of the sum. X and Y are real value random variables here. Sorry, I didn't specify that, but I'm like 80% sure I started it. Yep, 6 minutes in. Okay. So we proved that the sum of the expected values is equal to the expected value of the sum. We proved that the expected value of a constant times our real random variable is equal to a constant times the expected value of our real random variable. Then the combination of these two things proves this. Anyone remembers what this property is called? Linearity.
Why is it called that?
Because of linear algebra. You know what? If you come by after school, I think I could give it to you in a short enough explanation that you make sense of it. But you need images to see what's happening. So I bet you I can find a quick video that really quick made sense to you why we call that linearity. Anyways. And then the question we were ending with last time is, okay, let's ask this. Is the expected value of the product of the random variables equal to the product of the expected values of the random variables? And this is kind of where we left off last time. Good? Let's quick recap up to now. Anything here that doesn't make sense that we need to recover before pushing forward?
Again, it just feels kind of new, so I'm getting used to it, but I don't see anything that like really stands out. It doesn't make sense.
Okay. Maybe we'll go through, come back, reset, and then see if there's still something. Alright. So I need to remember not to erase anything as we go. For examples or
Wait, so
whatever.
this is all us?
Yeah. Lucky you.
Is this all of it, or is there more?
It's all of it. And we're already through a fourth of it.
Wow.
Time flies when you're having fun. Alright. So next, small little proof. And a little bit of terminology here. So if x is a 0, 1 random variable, you remember what a 0, 1 random variable is? All its right-hand values are either a 0 or a 1.
Oh, right.
That's what it means. So it either spits out 0 or it spits out 1, and that's it.
Failure and success.
We use them for success, failure, random variable.
Yeah.
So if x is a 0, 1 random variable, then the expected value of x is just equal to the probability that x spits out 1. Okay? Does it make sense what we're trying to prove? Alright, let's prove it. So let x be a 0, 1 random variable. Then, by definition, the expected value of x, not by definition, using this little theorem, the expected value of x is equal to the sum across all real numbers a times the probability that x is a. Now, there's only two a's that we care about here. What are the only things that x spits out?
0.
0 and 1. the probability that x spits out 7 is 0. The probability that x spits out anything but 0 or 1 is 0. So this has infinite 0 terms, only 2 terms that we actually care about, where x actually spits out the value, where there's actually a probability here. Does that make sense?
Yeah.
Okay. So, what are they? They're 0 and 1. So this is just the probability that x is 0 times 0, plus the probability that x is 1 times 1. Right?
Yes.
Yeah.
Which is obviously the probability that x is 1.
Huh.
Easy peasy. Good? Alright, moving on. Back to permutations. Your favorite. Alright? Do you even remember what a permutation is?
Can you give us the definition and don't come back?
A permutation. So, if you have a set, 1, 2, 3, a permutation on that set is a bijunction whose domain and image is that set. So, the simplest permutation is just 1, 1, 2, 2, 3, 3. There's a permutation on that set. Another permutation on that set. 1, 3, 2, 2, 1, 3. It just has to be
3, 1.
3, 1, thank you. 3, 1. In order for it to be a bijection, or in order for it to be a permutation, it has to be a bijection. And what's a bijection? 1 to 1 and on 2. So it has to use up all these values, 1, 2, 3. And it has to be 1 to 1, which means you can only use each value once. I can't have 1 goes to 3 and 3 goes to 3. Make sense?
Yep.
Okay, so that's what a permutation is. So I'll recap what a permutation is, and let's do some example problem work with permutations. And this is the notation that we used for all the permutations on an n-element set.
Right.
So let S of n be the set of all permutations on the set 1, 2, blah, 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 up to n. With me so far? Okay. And remember, we use pi as our dummy variable for some arbitrary permutation. So let pi be some permutation. And the probability of pi, we're going to say that each permutation is equally likely. And how many permutations are there on this set?
A lot. Or who knows?
Yeah, but what's the number?
Oh, it's n factorial.
N factorial. That's why we use factorials when we're calculating the number of permutations. It's not an accident. Right? So the probability of a particular permutation is 1 over n factorial.
Why was it n factorial again?
So let's kind of look at this case. Right? Here's my permutation that we haven't done anything to yet. How many options do I have for what goes here?
3,
How many for here?
2.
So there's 6 ways that I could fill that out.
Right.
3 factorial ways. And so S of n, there's n factorial things in there. So the probability of getting a particular permutation is 1 over n factorial. Okay? So in other words, the probability of me, if I were to randomly put in a 1, a 2, and a 3 into here, the probability of me getting this permutation is 1/6. The probability of me getting this permutation is 1/6. That make sense?
Yeah.
1 over 3 factorial.
I'm just confused. Why is pi?
Pi is not a number. Pi is what we use to represent an arbitrary permutation. Pi is a permutation. It's a function. So grab a random permutation out of there. Pi could be this thing. Pi could be this thing. It's just a random permutation.
Why didn't we come up with a different symbol?
We follow conventions already used. We don't pick our own conventions. Yeah, it's strange for you're so used to pi being a number. It's almost like having 3 represent a function to you.
Yeah.
Yeah. Okay, so continuing. So our set of all possible outcomes is all the permutations on this set, 1 through n. And the probability of a particular permutation is 1 over n factorial. So we just created our sample space, S of np. With me so far? Okay, so we have a sample space. Now we're going to create a random variable which gives us the number of fixed points in the permutation. What do we mean by a fixed point? A fixed point means it maps the number to itself. Not a fixed point is a fixed point is not a fixed point. This permutation had nothing but fixed points. This permutation had one fixed point. Okay? You with me so far?
Why do you all the fixed points?
It mapped it to itself. It didn't go anywhere.
Okay.
2 didn't go anywhere. It stayed there. So, x gives you the number of fixed points in a particular permutation. What we're looking for is the expected value of x. If I were to pick a random permutation, how many fixed points would I expect that permutation to have? I'm not asking you to answer, I'm just making sure you understand what we're looking for.
There could be 1 through n fixed points.
Yeah, there could be 0 through n fixed points.
Yeah.
It's real easy to have 0 fixed points. So the question is, if you pick a random permutation, how many fixed points do you expect it to have? You understand what we're looking for? Good?
Okay, so x is the random variable that gives the number of fixed points in pi.
Yeah, x is a random variable that tells us the number of fixed points in a particular permutation. So if we were to feed this permutation into x, it would spit out 3. If we were to feed this one in, it would spit out 1. If we were to spit this one in, it would spit out 0. Good? Okay, so that's what we're looking for. The expected value of x. We're looking for how many fixed points we can expect a random permutation to have. Okay? So let x give the number of fixed points in some permutation pi, and that's points where p of k equals k. It mapped k to itself. Good? In other words, we want to think about this as a sum of individual points. So let me try and make this make sense. I'll just go through this, and then if it doesn't make sense, we'll do it again. So in other words, x of pi is equal to the sum from k equals 1 to n. So we're incrementing through all the positions of our permutation. And we're going to add 1 if it was a fixed point, and 0 if it wasn't a fixed point. So this sum is going to be 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1. It's going to spell a 1 if that happened to be a fixed point at that location, and a 0 if it wasn't. So in other words, that sum, if we were talking about this one, would spit out 1, 1, 1. If we were talking about this one, it would spit out 0 plus 1 plus 0. If we were feeding this one in, it would spit out 0 plus 0 plus 0. So our random variable gives us a sum where x sub k of pi is 1 if pi sub k equals k at that location, and 0 if pi sub k does not equal k at that position. So x sub k is like a sub-random variable. We're making a random variable for each position, and then this random variable is a sum of all these random variables. You with me?
Yeah.
This isn't really a random variable. I shouldn't say that because its domain isn't S. The domain of this thing is S, but we're thinking about it. Actually, no, we could. We could, sorry. I shouldn't have said that. That's perfectly valid way to think about it. So we're defining this random variable in terms of n random variables like this.
Right.
Do we need to see something right now?
Sure.
So let's look at it in this case. In this case, we only have 3 positions. So I'm saying that x of pi is equal to x sub 1 of pi plus x sub 2 of pi plus x sub 3 of pi, where, what's the definition of x sub 1 sub pi? X sub 1 of pi is equal to 1 if, whatever that subscript is, pi at 1 is equal to 1, it's equal to 0 otherwise. So this thing is a 1 if it maps 1 to 1. This thing, if that were 2 there, this is a 1 if pi at 2 is equal to 2, etc. Does it make sense?
So, the parentheses there, pi at 2 is saying in the second position of permutation.
Yeah, what 2 maps to? What 1 maps to, what 2 maps to, what 3 maps to.
Okay.
If 2 maps to 2, then this position is a 1. If 2 doesn't map to 2, this position is a 0.
That's a fixed point. Right.
Right. It's another way of capturing the idea of fixed points. This is how we're counting the fixed points. Because that's what we want x to do. We want to count the fixed points. How are we going to make you count the fixed points with this? This is how we're going to define the function. So is this starting to make sense?
A little bit, yeah.
X of pi is equal to the sum of these smaller random variables, where this smaller random variable just checks its one position. X of k just checks, hey, when I throw k into pi, did I get a k out? If I did, I'm 1. If I didn't, I'm 0. And you do that for all k between 1 and n.
That's kind of complicated. Like, it's simple when you think about it, but like, it's a long way.
It's a lot of abstraction,
Yeah.
but it's actually really simple. So once it makes sense, it makes sense.
Like, it makes sense if you're like plugging into your computer, because then you can just do it. But it's just a lot of thinking. Sorry.
Yeah.
Well, we're intentionally trying to break this thing up into a bunch of random variables that are 0, 1 random variables. Notice each of these are now 0, 1 random variables. And we have this theorem for 0, 1 random variables. So that's motivating a little bit. So now we have x, which is not a 0, 1 random variable, expressed as a sum of 0, 1 random variables. Does that make sense?
It really does.
Really does. Well, that's a third of the class. Teacher has to get at least half the class. Who's going to get first out of you two?
Did I know?
The race is on. Okay. Let's come back to over here.
No.
I thought you, oh.
I got it kind of, but I'm not all the way there.
So let's write out each of these explicitly and start plugging in permutations. So x of 1 is equal to,
Can we write a permutation pi? So I can think about that.
yeah, I will.
Okay.
So we'll write this as equal to 1 if pi at 1 is equal to 1, 0 otherwise. X sub 2 of pi is equal to 1 if pi at 2 is equal to 2. Then it gives you a 1, otherwise it gives you a 0. X sub 3 is the same, but we won't bother with that. Now let's make a random permutation. Let's do x of a permutation. We'll have 1 goes to 2, 2 goes to 1. No, that's not it. We'll do 1 goes to 3, 2 goes to 2, 3 goes to 1. Right?
Okay.
So we'll say that's pi. So now x sub 1 of that same thing, I'm just going to write pi here. Plus x sub 2 of that same thing, I'm just going to write pi here. Plus x sub 3 of that same thing. Right?
Okay.
X of this is the same thing as x sub 1 of it, plus x sub 2 of it, plus x sub 3 of it. Put pi there. With me so far? Now, so I'm saying that x of pi, that same thing, not going to rewrite it out, is equal to x sub 1 of pi. What does x sub 1 of pi do? It plugs in 1 and sees if it gets out 1. If I plug 1 in for pi, do I get 1? No, so this first one's a 0. Plus, x sub 2, what do? You plug 2 into it and see if you get out 2. When you plug in 2, do you get out 2? Yeah, so x sub 2 spits out a 1. Plus, what does x sub 3 do? It plugs 3 into it and says, did you get out a 3?
No, you didn't.
No, you didn't, so that's a 0. So x of pi is equal to 0 plus 1 plus 0 is equal to 1. Ah, that permutation has one fixed point.
Okay. We just use so many x's. I'm getting it.
It's just, it's a
I'm
way
like,
to think about
I
it. It's not
know.
necessarily like, yeah, it's a lot of writing, but you only have to write it once and then it's in your brain to think about it.
So now x is x of 1 plus x of 2 plus x of 3 all the way to x of n. Where this just checks, did 1 map to 1? Yes or no? 1 if it did, 0 if it didn't. This checks, did 2 map to 2? Did 3 map to 3? Did n map to n? 1 if it did, 0 if it didn't.
Okay.
Good?
Yeah.
Alright. Woo! Okay. So, we know the expected value of the sum is equal to the sum of the expected values. So, the expected value of x, or the expected value of x1 plus x2 plus x3 plus x4 plus x5, etc., is the same thing as the expected value of x1 plus the expected value of x2 plus the expected value of x3, etc. So you good with how I'm going from this to this? X is equal to this sum, but the expected value of the sum is just the sum of the different expected values, using this.
Okay.
So instead of having the expected value of x1 plus x2 plus x3 plus x4, I can have the expected value of x1 plus the expected value of x2 plus the expected value of x3. So you good with what's happening here?
Yeah.
Alright, now we're just using this theorem up here. x1 is a 0, 1 random variable. Its expected value is just the probability that x1 equals 1. That's just probability that x2 equals 2, the probability that x3 equals 3, etc. And the probability that xn equals, equals 1. Why was I saying numbers?
Because yeah.
Yeah. Here it is. If x is a 0, 1 random variable, then its expected value is equal to the probability that x equals 1. So all of these can be replaced with the probability that the random variable equals 1. Right?
Okay.
Okay. Now, what is the probability that there's a 1 in the first place?
That there's one in the first place?
Yeah. What is the probability that when I fill this thing out, I put a 1 here?
1/3.
1/3, but in general it's
1 over
3
n.
factorial.
1 over n.
Oh. Oh, right. Yeah,
Right?
Yeah.
So, the probability that the first one is a fixed point is 1 over n. The probability that the second one is a fixed point is 1 over n. The probability that the third one is a fixed point is 1 over n, etc. So, the probability that we have a fixed point at each position is just 1 over n. So the expected value is the sum of those. So I'm doing 1 over n times, which equals 1. So what does this mean? This means you pick some massive number n. Doesn't matter. 100. You take all the permutations from 1 through 100,
Which are a lot.
which is, there's 100 factorial of them. You randomly pull one out. Chances are it has one fixed point and only one. It doesn't matter how many n's you have. If you pick a random permutation, you expect it to have one and only one fixed point.
Oh,
Really?
Yeah, that's what we just proved.
that's awesome.
The expected value came out to 1.
So then the expected value is always going to be 1.
For this was a very specific example. It's not always 1. The expected value can be tons of things. The expected value on rolling a 6-sided die is 7 halves if it's a fair die.
2? 6, 7,
7
8.
halves.
1.
Oh. Oh, yeah.
Huh.
Right.
That actually makes perfect sense.
Yeah.
Okay. So there's another example working with expected values and sums, and I want you guys to get more exposure to sums. Next one. Okay, so that was kind of the side example doing with sums. Now let's go back to this question that we were talking about. Is the expected value of the product equal to the product of the expected values? A very natural thing to do is to just kind of pick a sample space and see what happens, right? So let's pick a sample space and see what happens. So let's take the sample space for rolling 2 die. Let's let X be the outcome of the first die, and Y be the outcome of the second die. You with me so far? So if I roll a 2, 3, X is 2, Y is 3. You with me? What's the expected value of X?
Well, it's 7 halves.
7 halves. What's the expected value of Y?
Same thing.
7 halves. So the question is, when we do the expected value of X times Y, are we going to get 7 halves times 7 halves? Or 49/4? That's the question we have in our mind, right? So we write this out. What is the expected value of X times Y? Well, let's go through it all. How many ways are there to get a product of 1? If I roll 2, I'm multiplying the die together. I'm not adding.
Okay, so there's 1.
I'm multiplying. There's only 1.
Yeah.
Double ones.
Right.
That's the only rule. So 1 of your 36, so there's only 1, and there's 36 possible rules, so only 1 of the 36 gives you a 1. You with me so far?
Mm-hmm.
Continuing. A 2. How many ways can we get a 2? 1 and a 2 and a 2 and a 1. There's 2 ways that we can roll the die and get a product of 2. So 2 of the 36 ways. How many ways can we get a 3? 2. A 1 and a 3 and a 3 and a 1.
Right.
Right? And you keep on going doing all these. How many ways are there to get a 30? 2 ways. You can roll 6 and a 5, or 5 and a 6. And then how many ways are there to get a 36? 1. That's rolling a 6 and a 6. Good? Okay. I feel like this is confusing you guys a little bit for some reason. I'm not sure why. If we're just talking about the probability, if instead of adding the dice together, you multiply the dice together, then the probability of rolling a 1 is 136. Probability of rolling a 2 is 236.
Right.
Probability of rolling a 3 is 236. Probability of rolling a 30 is 236. Probability of rolling a 36 is 136. And you can do it for all the possible numbers that you can get out. And notice we're not going to do all the numbers. We're going to skip some, right? You can't roll an 11 in that example.
Mm-hmm.
You with me?
Mm-hmm.
Okay, so that's the expected value. Then you just add up all these numbers. I won't bother writing it out here, but it comes out to 441 over 36.
How did you get that?
Just, the book already has a chart on it.
Oh.
So I just wrote part of what's already in there. But you can just add up whatever the product of these are, right? 1 plus 4 plus 6 plus 60 plus 36. Comes out to 441 and divided by 36. Good? And this just so happens to be a perfect square. 441 is 21 squared, 36 is 6 squared, so that can be represented as 21 over 6. And 21 and 6 both have what in them? 3. And I wrote that wrong. That's supposed to be a 2. So divide top of 1 by 3, you ended up with 7 halves squared. Which is the expected value of X times the expected value of Y. 7 halves times 7 halves. It worked! Right?
Yeah.
So that means that the expected value of X times Y equals the expected value of X times the expected value of Y, right? So we can check that off. We proved it. Anyone questioning the proof? You better, because that's just an example.
Yeah.
No, we did not prove it. We came up with an example where it happened to work.
Yeah.
Let's look at an example where it doesn't work. Okay, so we have a fair coin, and we're going to just toss it twice. Nice and easy. X of H is going to be the number of heads. X of T is going to be the number of tails. What's the expected value of X of H? If I flip the coin twice, how many heads do I expect to get? I'm tossing the
0.75.
coin twice. How many of those do I expect to be heads? How many do I expect to be tails?
Probably the same thing.
One! If you flip the coin twice, you expect one of them to be heads and you expect one of them to be tails. You expect half your coin flips to be heads, you expect half your coin flips to be tails. Right?
I guess so, yeah.
You guys did not do what I asked you to do. Pretty obviously. Read your chapter. Okay, so pretty obviously, the expected value of heads is 1, but let's write it out all formal. We get 0 heads 1/4 the time. We get 1 heads 1/2 the time, and we get 2 heads 1/4 the time, right?
Yeah.
Or do I need to write out all 4 cases?
No.
What can we get? We can get heads, tails, tails, heads, tails, tails. Okay, there's all the cases.
Yep.
1/4 of the time, no heads. That's right there. 1/2 of the time, 1 heads. That's right there. 1/4 of the time, 2 heads. That's right there. Okay. And the expected value for tails, I hope you guys can keep up with that one. It's 1.
Yeah.
And throw something at you. Okay. However, the expected value of xh times xt is equal to, let's write it out. We can get 0 heads and 2 tails 1/4 the time. We can get 1 heads and 1 tails half the time. And we can get 2 heads and 0 tails 1/4 the time, right? You go with this is equal to that sum? Or do we need to refer to our red again? We can get 0 heads and 2 tails 1/4 the time. That's right there, and that's right there. Good?
And that equals 1/2.
And that equals 1/2. Yeah, 0 plus 1/2 plus 0 is not equal to 1, is equal to the product of the expected values. So it doesn't always work. So the question would become, did we just get really lucky here? Or is there some other condition that makes so it works? And yes, there is some condition that makes so it works. And that is if x and y are independent. Okay? So, if x and y are independent real random variables, then this is true. If they're dependent, it's not necessarily true. You might get lucky, you might not. In this case, they were independent. Right?
Yeah.
Knowing the rule of the first die does not help you know the rule of the second die.
Right.
In this case, they were not independent. Knowing how many heads does help you know how many tails there are. If you know x of h here, you instantly know x of t. They're dependent. If you know x here, you do not know y. It didn't help you in any way. You're still just guessing like you were before. It does make true sense how these are dependent and these are independent.
It makes sense that that's independent.
It doesn't make sense that this is dependent.
Yeah.
Okay, so let's think about this one for a second. I roll the dice. I tell you, x was a 5. What was y?
You don't know.
You don't have a clue. Didn't help you. Let's do this one. I flip the coin. I tell you, there's 1 heads.
Well, you could guess there's a tails, but like, you don't know.
What else could there be if there's only 1 heads?
If you flipped it twice.
I flip it twice and there's only 1 heads. There could be a tails. Maybe that sneaky coin landed on its side.
Okay, I guess that makes more sense.
Click.
I was thinking like you have 2 coins.
It's just like the example we did
The other one's heads, tails.
over here with your other one. Okay. So, independent, and this works. So let's prove it. Let's prove that this works when they're independent.
Okay.
Lots of sums. Hope you're ready for this. Alright, so if x and y are independent real random variables, then the expectation of the product is equal to the product of the expectations. Good?
Yeah.
Well, you understand what we're trying to prove is what I mean. I'm not saying let's continue. Okay, so I'm going to create some dummy random variable to represent the product. Z is equal to x times y.
Okay.
And so we're trying to prove that the expected value of z is equal to the expected value of x times y. And we're done.
We did it.
Almost. We just skipped the middle part.
That's some middle part.
Yeah, lots of sum in there. So, the expected value of z is equal to the sum over all real numbers of a times the probability of z being gained. Good? So, we know that much at least. Now, since x and y are independent, then the probability that z is equal to a is the same as the probability that x is equal to b and y is equal to c, where b times c equals a. Z is x times y, right?
Okay.
So if z equals a, then that means x times y equals a.
Okay.
So that means the number that x spit out, namely b, and the number that y spit out, namely c, their product was a.
Okay.
Okay? So the probability that z equals a is the same as the probability that x equals b and y equals c for any numbers b and c where their product is a. For example, let's say that a is 3. This could have been 3 and 1, or it could have been 1 and 3. There were two cases there that we need to add up.
Okay.
Still no? The probability that z equals a is the same as adding up all the b's and c's that x and y spit out, where their product was a. Did that say it better?
Do you guys get it?
No. We're not good.
Why is expected value so hard?
Confusing.
I
We
don't
don't
get
know.
Okay.
it. It's such a simple concept.
Over here, the expected value that z, or x times y, was equal to, let's pick a number.
36.
No, pick a more middle one.
One.
Middle one?
20.
Let's do 6. Not the expected value, sorry. The probability that x times y equals 6 is equal to, I'm going to need a write smaller because it's going to get kind of big. The probability that z is equal to 6 is equal to the sum of all the AB's, not AB's, we'll do BC's. BC's in R, where BC equals 6, of the probability that x is equal to b and times the probability that y is equal to c. So let's write this out. So there's using the notation over there. I'm going to rewrite the same thing out, except for this time more of a manual way. That is the same as the probability that x is equal to 1 times the probability that y is equal to 6 plus the probability that x is equal to 2 times the probability that y is equal to 3. That's the probability that x is equal to 3 times the probability that y is equal to 2 plus the probability that x is equal to 6 times the probability that y is equal to 1. Right? These were all the ways that x times y equals 6, right?
Because of that property.
Well, we're just calculating this. Calculating this is the same as calculating this sum.
Is it because of that? Because no.
We're not saying it because, we're just saying how you would do it. If I said, find the probability that x times y equals 6, what would you say in your head? You say, okay, how do we get a 6? We can get a 1 and a 6, we can get a 2 and a 3, we can get a 3 and a 2, we can get a 6 and a 1. Those are all the rules you can do that whose product spit out a 6, right? So we just need to do the probability of those. We do the probability that your first dice is a 1 and your second dice is a 6, plus the probability that your first dice is a 2, second dice is a 3, plus the probability that your first dice is 3, and your second dice is 2, plus the probability that your first dice is 6, and your second dice is 1.
And what's the probability of all those?
Well, whatever they are, I mean, we can check. Each of these is just 136, right? In this case.
Yeah.
So the probability of rolling a 6 is 436, which is, we didn't write that there because we stopped.
Wait a minute. Not 436.
Yeah, there's 4 rolls that give you a 6. So 4 of your 36 possible rolls gives you a 6. So there's a 436 chance that if you roll 2 die, the product will be a 6.
Okay, wait. 36. You don't have 36 rolls.
There's 36 possible rolls when you roll 2 die.
Oh, yeah, I guess that's true. Okay.
Good? So,
Wait, no. That's wrong again.
what's wrong again?
Wouldn't that only be 6?
Wouldn't what only be
If
6?
you're keeping it as 1 roll, there's only 6 chances for one and 6 chances for the other.
There's 6 chances you get this, and there's 6 chances you get this, right?
Yeah.
So this is a 1 in 6 chance, this is a 1 in 6 chance.
Yeah.
What's 1 6 times 1 6?
Why are they times?
That's exactly how I wrote them.
Sure it is.
But also because they're independent variables, so the product of rolling a 1 and a 6 is the same as
True.
rolling a 1 times
Okay.
rolling a 6. Sorry, I didn't say that right, but I think you understood it right. Okay, so you good with the probability of xy equaling 6 is the same as the sum of these probabilities.
Yeah.
So we did the sum of all the real numbers BC that you can get their product equals to 6, the probability of those. So if B and C are 2 numbers such that their product equals 6, calculate the probability and add it up. That's the probability of getting a 6.
All B's and C's. Huh. Because there could
All
be
the
like,
B's and C's whose product is 6.
Because there could be 3 different pairs of B and C.
Yeah, in this case, there were 4 different pairs of B and C, right?
Right. Okay, that makes sense.
So you're adding up the probability of all the cases where B and C equals 6.
Yes. That is exactly right.
I think I gotcha.
Adding up. That's exactly right. Okay, so that's what this is saying. The probability that Z is equal to A is the sum of the probabilities of B's and C's whose product is A.
Wait, what?
Okay.
So are we good with this line?
I think
Yes.
so, yeah.
Okay, so we're going to make that substitution. So now our expected value, instead of it being the sum, we're going to substitute this with this. Notice the probability that Z equals A is that thing. So we're going to take this sum and stick it there. That's what we did here.
Okay.
Simple substitution. Haven't done anything else. You good to here?
Yes.
Wait a minute.
We'll wait.
Oh yeah, okay.
Okay. So now we have A times a sum. We can distribute that A through this whole sum. And that applies A to each term in the sum.
Which you didn't do.
Yeah.
What?
So if I have 2 times the sum from K equals 1 to, where should we end? 3? K equals 1 to 3 of K. This is equal to 2 times 1 plus 2 plus 3, right?
Yeah.
And I'm saying that is identical to the sum from K equals 1 to 3 of 2k. That's equal to 2 plus 4 plus 6. We just distributed the 2 to all the terms.
Huh,
Pretty crazy.
that's cute.
Insane. Alright. So that's all we're doing here. We have a times the sum. We're distributing the a to each term in the sum. Alright. So we're good from this step to this step, right?
I'm still kind of tripping out that we're
It's really,
timesing two sums.
it's tricky.
We're doing a sum of sums.
Yeah.
We're not multiplying the sums.
Right.
Even if you're not multiplying, the sum of sums is,
A sum of
It's
sums.
messy.
That sounds like a scary movie. Doesn't it? Okay, keep going.
Well, no, we can't keep going if you don't understand the sum of sums.
We're supposed to understand it already?
Yeah, you're supposed to understand the sum of sums. So let's do a sum of sums.
we were never taught that.
Yeah, you never even introduced it.
Well, it should be pretty.
We'll do the sum from I equals
Oh.
1 to 2 of the sum from k equals 1 to 2 of I times k. Right? That's a sum over a sum.
Okay.
Okay? So now, this is equal to, let's do when I is 1.
Okay.
That's 1 times the sum, sorry.
Oh, that's gross. That's wait, what
So I expanded out the outer sum.
That's my secret, yeah.
There's only 2 terms in it.
I know.
There's that term and that term.
Yep.
And now I'm going to expand out the inner sums. Oh, sorry. That 2 doesn't go there.
Where does it go?
The i's on the inside. It doesn't go on the outside. I was including the I twice.
Yeah, I was wondering about that.
Good wonder. And that's it expanded out. So we expand out this sum, which is
Wait,
this.
what? Are you gonna explain it?
Well, plug in 1 for k, what do you get? 1. Plug in 2 for k, what do you get? 2. So 1 plus 2 is that sum. This is plug in 1 for k, 2. Plug in 2 for k, 4. So this is that sum.
Okay.
So it's just sum, and you sum them up. A sum of sums.
It's really just order operations.
It's more of like a grouping. It's
Yeah.
just a particular grouping. We have an inner, we're grouping some inner terms. We group those together and we group those together and we sum them. Okay? So where did we die? I can't remember where we were at. Where it stopped making sense.
Just say the one down.
Right here?
There's the third one.
So we were going from here to here.
That's fine.
No,
We
that
get
was when
that.
we distributed the A and.
Okay, so first off, let's go from here to here again. Okay? Because that's when we introduce the second sum. We're saying that this probability can be represented as this sum right here. So instead of summing up A times these probabilities, we summed up A times these sums.
Right.
Right? And then we distributed the A into each term of the sum, which got us to here.
Right.
Good? Okay. Now, A is equal to B times C.
Whoa. Okay.
Yeah, it is.
Yeah, it is. So we got our BC there. Now, going from here to here, we're getting rid of our inner sum. We're basically saying, let's get rid of all these parentheses now. So instead of viewing it as a sum of sums, we're getting rid of the parentheses and just viewing it as that big sum, whatever it is now.
What is it?
From here to here. It's like erasing these inner brackets. So now we're just summing up all these BCs, whatever they are. This is summing up the BCs in particular order. It's summing up the BCs where they summed up where A was 1, then where A was 2, then where A was 3, then where A was 4. Now we're just summing them up. We don't care about what order. We're just getting rid of our inner grouping. It's like what I had before, right? We had 1 plus 2 plus 3, or 2 plus 4 is what we had, right? Remember?
Yeah.
And we were doing it in a grouping. We were grouping where I was 1 and where I was 2. Here we're doing a grouping where A is a particular value on each one. Where A is some value, then the next A some value, then the next A some value.
Okay.
Now we're saying let's get rid of these parentheses. We don't care about them anymore. We don't need to preserve when I was 1 and when I was 2.
But it's not really parentheses, is it?
Yeah.
Right, because it already was summed in.
It doesn't matter what order you sum. Ultimately, you just have a big sum. So a sum inside sums is still just a sum.
Who knew plus could be so hard?
You're just getting rid of your parentheses. This is just doing a particular sum first, the parentheses. Right? When I put the parentheses around that, that's just saying add 1 plus 2 first. Add 2 plus 4 first. But that doesn't really matter. I can add 1 plus 2 plus 3 plus, or 1 plus 2 plus 2 plus 4. I can just do it however I want.
Right. I get that.
That's all we're doing from here to here. We're saying erase parentheses. So now we're just summing up all the BCs in R, where we had these probabilities.
So are you getting rid of just the outside one?
I'm not really getting rid of the outside one. I'm getting rid of grouping by when the product was a particular value. I was doing where A was equal to 1 here. So all the ones that multiplied to be 6 were first. And then all the ones that multiplied to be 7 were next. And all the ones that multiplied to be 8 were next. Or something like that.
Okay.
I'm saying forget the order.
I understand like that's what your concept is. I don't understand how that's what that actually is.
Well, now we're just talking about the probabilities of the probability that X is B and Y is C times their product. That's the same thing as the probability of A times A, kind of, right? I mean, this should look almost identical to that thing. We're summing up across all our BCs instead of our A's. A times the probability
Right, yeah, it does.
that Z equals A.
Because Z equals XY, right? Oh, that's what we're trying to prove.
But it's just more split up now because there were a lot of ways to get this A now. We're not grouping by A's anymore. Okay. So now we're no longer doing it in any particular order. We don't have any inner grouping.
Okay.
And the reason we did that is because now we're going to start adding a different inner grouping.
Okay.
So now, start by grouping by all the B's are a particular value. So for every B, then for every C, do the sum. So we do all the ones where B equaled 1 first, and then all the ones where B equaled 2 next, and then all the ones where B equaled 3 next. Okay. We're just grouping them together. It's just a regrouping.
Yeah, it's definitely the summations. Because I get what you're saying.
And I also, you might notice, I associated the B with the B and the C with the C, but order doesn't matter for multiplication. Right? Okay. So now, I need to factor out. Notice for each one of these, how can I say this right? This B is dictated by this outer sum. So I can factor out this part from this sum. This never changes on this inner sum, right? On the inner sum, my B never changes. Okay. So C, for every real number, so pick a b, 7. Then c, through all the real numbers, we leave b at 7. So it's 7 times the probability that x equals 7 times, and then we're plugging in for c every real number. And we're adding those up. That's what this inner sum's doing. Right? So since the b's aren't changing, they're a constant in this inner sum. So we can pull them out. Do you program?
Yeah.
If you program, you can think about like a for loop inside a for loop.
I don't really, but I get what you're doing. Alright, that makes sense.
That makes sense? Okay. So we factor this term out of each of the inner sums. And we have it like that. And now, the sum of all the c's is always going to be the same thing. If I go over every real number, grab a c, and do c times the probability of getting c, then for every b, that's always the same thing. So now I have a sum of this times a constant. This is always going to come out to the same thing, regardless of what b is. So in other words, what I'm saying is, this thing, c, for all the c's and r's, c times the probability that x equals c is going to be a number.
Why?
Because there is some probability.
Okay, so that makes sense.
So say that equals some number a. Then this sum right here, we can rewrite as, this is a sum over every b in r of b times the probability that x equals b times a. Because then we do that again. Pick a b, we're doing that sum. Pick a b, we're doing that sum. And it's the same no matter what our b is.
Okay.
So it's always the same thing. So we can factor it out. And instead of writing it ahead of the a, we're just going to write it behind the a. So we're going to like do our sum and then multiply when we're done adding. Does that make sense? So that's what we're doing from here to here. And we're done. And once again, the best way to wrap your head around this thing is to pick some case, to do some actual example, and write out all the sums each time. And you can pick a simple example. Yeah, I think it still helped you a lot.
Probably.
So just do like, for coin flip twice, have x be the first coin flip, and it's 1 if it comes up heads. Y is the second coin flip, and it's 1 if it comes up heads. Write out the sum.
Last step.
Okay, you know what? Let's just grab the bull by the horns. And I will do a physical example as we go, step by step, for each of these.
Okay.
So that you can see exactly what's happening. We'll come back into that. I'm going to need you erase. So we'll cover this and we'll go back to that. Well, let's just do what I said at the beginning. Let's cover everything, then we'll go back, and that way I can erase as we go. So, let's continue. Last concept we need to cover is variance. Now, the intuition for what variance is meant to capture is how close your data is together. High variance means your data is all over the place. Low variance means it's very contained. So that's the idea it's meant to capture, so let's look at it. So let x be a real random variable, and let mu be its expected value.
Why are we using mu for that?
Because we're going to be, variance is an expectation, and we don't want to do expectation inside expectation. I don't want you to get confused. It's common notation so that you're not doing an expectation of an expectation.
That makes no sense.
It's just shorthand. But mu is used as, this is a common variable for the expectation.
Okay.
Alright, so just stick with it for a second. I think when we do proofs with it, you'll see why it helps keep things clear. So let mu be the expected value of x. The variance of x, remember variance once again, like expected value, it only makes sense if what you're plugging in there is a real random variable. The variance of x is equal to the expected value of x minus its expected value squared.
Okay.
Now, the thing that might seem weird to you is, why are we squaring it? Why isn't it something like that?
Well, the whole thing that doesn't make sense is I don't know variances in the first place. So.
We want to capture how off is our data. So let's look at an example, then we'll go back and talk about variance again and do it all in one go. So we'll calculate the variance of some things that we'll talk about again. So let x minus z be random variables such that x spits out 2 50% of the time and negative 2 50% of the time. You with me?
Okay.
So we don't know what s is, but whatever s is, x spits out 2 half the time and it spits out negative 2 half the time. Y spits out negative 10.1% of the time, 0 99.8% of the time, and 10.1% of the time. And z spits out negative 5 1/3 of the time, 0 1/3 of the time, 5 1/3 of the time. You with me?
Wait. Oh, yeah,
Okay.
Sorry, those are lines above the threes.
Well, that makes sense.
So the intuition is all this data is really close together for the most part.
Yeah.
99.8% of the time it's just a 0, and occasionally you have an outlier. But for the most part, the data is really close together. This one, the data is kind of just back and forth. It's kind of close, but it's back and forth a bit. And then this one, the data is jumping around quite often. Right?
Okay.
I mean, if you were to plot this data on the number line, when we're plotting this thing over here, then we're going negative 2, 2, negative 2, 2, maybe plot above and below so that you can see it. And the data kind of looks like that, right? For this one.
Yeah.
For this one, the data looks like all right there, tons, 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 with one out there and one out there. So the data is all close together on this. The data is kind of close together on this. And on this one, we've got a good amount of data out here, we've got a good amount of data right here, and we've got a good amount of data right here. This is the most scattered, this is the least scattered, this is the middle scattered. So variance, intuitively, is trying to capture how scattered is your data.
Okay.
That makes sense?
That's weird, but yeah, it makes sense.
That's really need to read the chapter.
I just need
To help motivate some of these things. Okay. So notice that for each of these, the expected value is going to be 0. The expected value of x is 0. It gives 2 half the time and negative 2 half the time. What's the average of those?
0.
The weighted average of those is 0. The weighted average of those, 0. The weighted average of those, 0.
Right.
By the way, that's another way you can think about expected value. A weighted average. Expected value.
What's the
Same
weighted
thing.
average?
A weighted average.
I know an average. What's the difference between an average and a weighted average?
Not everything counts equally, so if you're taking a class and I weight your test 80% and your homework 20%, then you need to accommodate that. You can't just say, what's my grade in the class? Well, let's see. I've got 100 on my homework and I've got 20% on my test, therefore my grade is 60%. No, you need to do a weighted average of those. You need to weight this by 0.8 and you need to weight this by 0.2.
So how do you do the math on that? You multiply?
Well, you would add it then. So if you have let's say that was your homework and this was your test. Homework is 20% of your grade, test is 80% of your grade. Let me write parentheses so that you understand what I'm saying. Homework is 20% of your grade, and tests, which you have 20 on, are 80% of your grade. Then your grade in the class is going to be 20 plus 16.
So
That's not right.
So you're getting a 36 in the class.
you don't divide it at all?
You got 20% on your test, and they're 80% of your grade. Well, we already divided by making that,
Yeah.
if we looked at 20 and 80 and then divided by 100, would have been doing the average, how you expect an average to come out. So we kind of were averaging as we went by using percentages. But yeah, so.
Oh, okay.
Anyways, back to what we were talking about. So the expected value of this, 0. Expected value of this, 0. Expected value of this, 0. It's just as likely that you get over 0 by the same amount and under 0 by the same amount. Is it obvious to you guys that the expected value of each of these is 0?
Should be.
Yeah, it should be.
I'm still
Even just looking at it,
just trying to remember what the expected value is.
intuition for it. So here we say, you get 2 50% of the time, you get negative 2 50% of the time. Right? So if you were to have, let's turn to a game. We're playing a game. Something that's 50-50, flipping a coin. You flip heads, you get $2. You flip tails, you owe me $2. You play the game 1,000 times. How much money do you expect to have? 0. When it's all said and done, you would have expected to made and lost $0. It's just as likely that you would have made money as you would have lost money. Same thing if we set up a similar game here. Same thing if we would have set up a similar game here.
I see. Because every time you get 5, you get negative 5, so it cancels
Right, it's
out.
just as likely to get negative 5 as 5. Those cancel out.
Right.
Because remember when you calculate, calculating the expected value is 2 times that plus negative 2 times that. Negative 10 times that plus 0 times that plus 10 times that. Negative 5 times that plus 0 times that plus 5 times that. If you were to explicitly calculate. 0, 0, 0. So they're all 0. So mu, the expected value of each of those is 0. With me?
Yeah.
So now let's calculate the variance on each of them. So the variance on this one. That's the expected value of x minus mu squared. Now,
Mu.
mu. That's the name of that letter. It's a Greek letter. Mu.
Okay.
So, the expected value of a sum is the...
What?
Oh, sorry. I thought I was doing something I don't know. Mu is 0. X minus 0 is?
X.
Squared is x squared.
Okay.
So now let's calculate the expected value of x squared. We get 2 50% of the time, so 2 squared 50% of the time. Negative 2 50% of the time. Right?
So where's the square there?
I'm calculating x squared. The expected value of x squared. X is 2 50% of the time, but I'm looking for x squared.
So why are you squaring x? And why are you squaring the x minus mu?
Oh, so why is it this? Why is it squared instead of something like that?
Yeah.
We'll come back to that.
Okay.
But first I want to just show you how this gives us how much the data in some ways spread out. Anyways, x squared, but you see that the expected value of x squared is this. Nothing weird there?
Yep.
Good? Which is 4. Okay, so let's do it for y. The variance of y is equal to the expected value of y minus mu squared. Mu is 0, so that's just y squared. So calculate the expected value of y squared. Negative 10 squared times the probability of negative 10 plus 0 squared times the probability of 0 plus 10 squared times the probability of 10 comes out to 0.2. Good?
Wait, oh, right.
Because you have 100 times 1,000 is 0.1, and then 100 times 1,000 is 0.1 again, so 0.2. Because that one's just 0. Right?
Yep.
What's throwing you off? Y has these 3 values. It's negative 10, 1% of the time, or 0.001.
I understand.
Oh, was it going for a percent to that?
No.
No?
My understanding of expected value, it makes sense for x, y, and z, and then I try and use it in the equation, something like that
It's
or
not
that, and it
expected
kind of
value.
just loses its meaning. So then we go through and we're like, expected value of this, and I can kind of,
It's all the outcomes times the probability of that outcome. the outcome times the probability. Sum it up. So it's the sum of that times that plus that times that plus that times that.
Okay.
That's what expected value is. That's what we have. That's this way of thinking about it. For every A that we have a probability for, it's a probability of A times A. So negative 10 times the probability of 10 plus 0 times the probability of 0 plus 10 times the probability of 10.
Can you say that one more time? What you just said?
The expected value is equal to the sum of all the probabilities. So, first off, because this is really doing an infinite sum over every real number.
Right.
So for every real number, if there's a probability that x can be that number, do the probability that x can be that number times that number. Sum those up. That's the expected value. Because most times it's just going to be 0. Right?
Okay.
Because 9,276 is a real number. What's the probability that x equals 9,276 in our example? It doesn't. It can only take on 2 or negative 2 in this example, negative 10, 0 or 10 in this example, negative 5, 0 or 5 in this example. In all other cases, it's 0. That's why that book was having you do the problems it was having you do. It says calculate the expected, or calculate the probability that x equals m for all integers m. And you're saying most of the time it's 0, and then in these few cases it actually had a value. Right? On the homework problem we did right before class. Same thing here. For most A's, the probability is 0. And then there's a finite number of A's that our expected value actually can spit out. Not our expected value, our random variable can actually spit out.
Right.
Because the expected value, the random variable, only has so many outputs that spits out. Spits out a finite number of outputs. So there's only so many A's that there's actually a probability for. Every other A is 0. So, yeah, that's how you calculate the expected value. It's the sum of all the numbers it can spit out times the probability that it spits out that number. Good?
Yeah.
So,
I just don't,
we calculate the different variances, just don't what?
I don't know how you find the expected value.
We just found the expected value of all three of those. 0, 0, 0.
Yeah, but that's easy.
We found the expected value of those squared. 4.2 and 16.6 forever. We found the expected value of x squared. We know that the expected value of x is just 0. Now here's the expected value of x squared. Here's the expected value of y squared. Here's the expected value of z squared. Anyways, so the variance, the numbers that we get, follow our intuition. This data was the most spread out, this data was the least spread out, this data was middle. Most spread out, least spread out, somewhere in between. So that's what we use variance for. It's some sort of metric for how spread out the data is. Now, if you get rid of the square and you just do that, and you want to calculate the variance like that, so you're saying we're going to take a weighted average of how far x is from the average, and average all those up.
I missed that.
So this is the average x spits out. It's its expected value. It's average. So if we just do x minus its average, and we average those. Think about the expected value function as an average. That's what it is. It's an average. So we're averaging the difference between these. Between x and x's average. You with me?
Okay.
If we were to do the expected value of x minus its average, that's always going to come out to 0.
Say that again.
if we were to do, let me try to say it like this. If we were to average the difference between a set of numbers and their average, we'd always get 0. Let's look at an example. Let's say that we're averaging the set 10, 1, and 5. Sorry. 10, 0, and 5. That way 5 is also the average. The average of these numbers is 5, right?
Yeah.
But if I average up each of these minus the average, so I average up 10 minus 5, plus 0 minus 5, plus 5 minus 5, and if I average all those up and divide by 3, I'm still going to get 0.
Yeah.
So if we were to just leave it like that, we get 0. So we square whatever difference we get between them. That way we get a positive number. It gets rid of all the times where this could have come out negative. I mean, there's no reason that you should be able to look at the data and say, oh, based off just looking at the data, the variance is blah, 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 blah. It doesn't have any meaningful notion like that. It just gives you an idea of this data is more spread out than this data, is way less spread out than this data. In essence, what we were doing is we're saying that point's the average of the data, and let's have the data spread out around that point, like this.
Okay.
Intuitively, what we were doing is we were finding the distance between the average and that point, finding that distance, squaring that distance, and continuing on our merry way. Finding the difference between the average and this point, squaring it, and adding it, and doing that here, and here, and here, and here, and here. And the reason that we're squaring the distance and adding it is so that we don't get negative numbers. Because if the distance here was 5, then the distance here might be negative 5. And then they cancel each other out. And so you end up with 0. Sorry, you don't have negative distances. I'm trying to just give intuition. But what it gives you is a notion for how to calculate this. So you should know for sure, A, how to calculate the variance, even if the number doesn't really mean anything to you. And then you should know, based off of the variance, that, well, 16, that's real scattered out data, and 0.2, oh, that data is real close together. There's no real intuition for it outside of that.
Okay.
All right. Last thing we're going to do, come up with another way to calculate the variance. This is actually the formula that I knew from probability and statistics. I'm sure that we were taught that, but if you were to Google a formula for variance, I bet you that you get something that looks like this. But the variance is equal to the expected value of x squared minus, how can I say this? The expectation of the square minus the square of the expectation also gives you the variance. So here's the definition for variance. Now we're proving that this is another formula we could use. Just like what we did over here, we said the expected value of x is this, but here's another formula that you can use if you want to. Another way to think about it. So this is a definition of variance. Here's another formula that we can use to calculate variance if we want to. So let's prove that those are the same. So the variance of x is just equal to this. That's the definition, where mu is just the expected value of x. Okay. Right? X minus mu squared is x squared minus 2x mu plus mu squared. Okay. That's pretty straightforward, right? Yeah. Now we have an expectation of a sum.
Why is that a sum?
We have this plus this plus this.
Oh, okay.
So we have an expectation of a sum is just the sum of the expectations. And -2 is just a constant, and mu is just a constant, so I pulled them out. And I'm combining these rules over here. Or you can think about we're just using linearity. Linearity tells us that if you have a constant times some random variable plus constant times some random variable, you can pull the constants outside the expectation, and you can do the sum outside the expectation. Does that make sense? A and B here are constants. X and Y are random variables. So the expectation of a constant times a random variable plus constant times a random variable, and we arbitrarily have two terms here, but we could have n terms here, doesn't matter, is the same thing as this. We can pull the constants outside the expectation, and instead of doing the expectation of the sum, we can do a sum of expectations. Does that make sense? So that's exactly what we're doing here. We're splitting this up into three different sums. The expectation of that, the expectation of that, the expectation of that. And then negative 2 times mu is just a constant. And I didn't want to do the expectation of just 1, so I left the constant in here. But I could have pulled it out. So I could have pulled that mu squared out. I think it makes more sense if I don't do it to continue. But you good with this to this and this to this?
Okay.
Maybe this to this one feels a little bit weird, but we'll show that I could have put a 1 in there and it would have done the same thing anyways. So now, just calculating, what is the expected value of x? That's just mu. By definition, where mu is expected value of x. So I'm going to replace that with the mu. There. Good?
Yeah.
And then the expected value of a constant is just going to be that constant. Right? Okay, so that's what we're doing from there to there. So now we have the expected value of x squared minus 2 mu plus mu is just the expected value of x squared minus mu squared, which is the definition of u of x. Whereas mu was a variable for u of x. So there we go. So that's the proof that that's another way to calculate the variance. And there we go. So that's that. Go on break. When you come back, we'll go over any questions that you have. And then if there's no more questions with that, then I want to do a little bit of prep work with you guys before next week for special relativity. Give you some basic physics vocabulary.
Okay.